Can you make me the co-host?
Yeah, I will.
So is my voice clearer than earlier? So, or is
Yes,
it too loud?
it is. Yes.
Is it too loud, or should I like
No, no,
decrease the
it's fine.
intensity? Okay.
How are you?
Oh, better, better.
Okay. Yeah, a bit too slow today. People joining in. Don't know why. Usually, I have people much earlier.
Yeah, true. Even Madhugar is not here.
Correct. Ah, we are the only three here.
Yeah, till now.
Till now, yes. I'll make him. Do you keep your video usually off even when you speak? I thought.
Yeah, it is off, I guess, because like there might be some disturbance from the background, so I just keep it off. Like, do you want me to turn it on?
I don't know. I mean, there is this thing that I have. Maybe speakers' expressions are important. I don't know.
Maybe.
Probably not. Probably not.
No, I
Maybe
think
the
it is.
audience is
I
up.
think it helps. Yeah, I think it helps.
Yeah.
In fact, it helps the viewers express. I mean, the audience expressions are also important.
Also helps. I think so. I think.
Yeah, if everybody, like many people turn on their video, then I mean, it seems pretty natural to turn it on. But otherwise, it feels a bit weird to me, at least. I don't know. Maybe I'm not like used to it.
See, but then again, even if all the audience beyond, there are lots of people. It is hard. Will you be able to watch them all? I mean, you have.
No, of course not. But like even presence of some people like that might help. So I think they have an exam on Saturday, the DS people at least. So
Which subject?
some people have it. I don't know, like algorithm or something, I guess. Okay, they very
I
few
think
people are
now
here.
we have enough
Yeah.
people. So start at 3:35, 5 minutes we're given time. Yeah, 1 more minute.
Just okay. Let's wait for 1 more minute and then we
Yeah.
shall start. Okay, so let's start. Let me share my screen. Okay, so it's visible, right?
Yes. Yes.
Okay. Okay, so today we're not like I didn't make slides because we have to go to the code and I'll explain the code and we'll talk about this like a bit of TensorFlow and NumPy, and I will start by like reviewing something which we missed last time. So last time like I went very hurriedly through all of this. So let's start with this backpropagation. So, I mean, I'm not going to do it again, but I will just, first of all, I wanted to show an example because Professor Shiva said that it's better to do it. So can anybody like speak, like unmute your mic and tell me that whether they need, like, they're confused for this, how to perform this backpropagation? Or you all have like a firm like understanding of that how you actually implement it, or and not implement in Python, I mean at least how to manually perform this backpropagation. Shomodev, can you speak? Can you unmute?
Yeah, I'm okay.
Yes. Okay, so if everybody like understood that backpropagation, then Professor, do you think I should like give an example or we should move ahead? Because
Yeah. So the question, I guess, is if everyone understands the basic steps of, there are two questions. Okay, one is how the actual propagation works, as Hitarth showed last time. So that is one part of the question. Okay. The other thing is, how it works on a, how the chain rule. I mean, that it, are you convinced that this way of back propagation indeed computes the differentiation, the partial derivatives of the cost function? Okay. And number three, he also Hitak also pointed out this, how the training data, large training data, rather than running the back propagation all at once in a monolithic thing, the thing is partitioned into smaller sets. Okay, so if you all have any questions on that, and if you are, then it may be worth going through a simple example quickly. If they are all comfortable with with these three and they don't have any questions with respect to the questions that I raised, then we will, then you can go ahead. Okay, so that's what I'm going to ask. If anybody wants Hitat to go through an example just to refresh your memory, yell at this time. Otherwise, you can go ahead. So I think it's up to them.
Okay, so like I'll wait for like, let's say, for a few seconds to see if anybody has anything to say.
Otherwise, I don't mind if you. Okay. So I guess.
Okay, so I think we should.
Okay, so you can then go ahead with your plan as scheduled. Yeah.
Okay, so still I'll just revise, like just give you one recap. So this, I have built the slides and I think they're available on Moodle, so you can go through that. So these are the same slides. I'm just walking through it again in, like, let's say, like, I'll try to do it in 10 or 15 minutes. So just for a recap, I think here there was some, like, something was messed up. So the point is, you calculate dc by d1 and then you go backward and you keep on calculating these derivatives, and then you multiply them and take the summation, and you'll get the gradient of dc by dw1, and you do it for all the weights and all the biases. And that is also this time the main goal of this lecture is to give you this idea of how to do the assignment and what we are expecting in the assignment. So I will let more questions and I'll tell you what exactly you need to do, at least in the first part of the assignment, and the rest of it you have to figure it out on your own. Okay, so let's go through this SGD, stochastic gradient descent. So maybe, I mean, as I told you, I mean, I was hurrying last time. So in the main point of this SGD is that if I have a big training set, so let me try to draw it. Okay, so let's say I have a really big training data for me and with me, and if I'm calculating the gradient for this whole thing, then what will happen, it will take a lot of time to go through all of this. So let's say there are 10,000 examples here, and I go through all of them. And if you remember, in the algorithm that I described for backpropagation, you first of all calculate the gradient with respect to each example. So gradient is not calculated, the backpropagation algorithm is not working on the training data as an array, or though there's a possibility that you can implement the algorithm in such a way that it acts on the whole data simultaneously, or at least on a large amount of data. But for now, the way we have described it, it works on one single example. So you have one example, let's say this example x comma y, and you feed forward it, and then to your network, and then you do the backpropagation, and you get the gradient. So you get some matrices, or let's say column vectors, if you are familiar with that one, which is basically nabla of all the weights. And then you subtract this thing. You update the vectors, weights, w equal to w minus some s times nabla w. So this is what you do. And that will give you the updated weights. And actually, so yeah, this is what you actually do if you are training on per example basis, like you are training on for each example. But if you're doing it for the data, for the big data, let's say there are 10,000 examples, then you sum up these nabla w's for all the examples, and then you perform this one step, and this gives you one single update. Now, the consequence of this is, so if I have the loss function, so if the loss function is L, let us just call it L. And as you remember, it was summation over all the examples. So I sum the cost over all the examples, and then I get the total cost. Let's call it cost, because maybe that's what I said earlier. It's also called loss. So this is the cost, the total cost over summation over all the examples, and then you are trying to reduce this cost. So if you draw the graph of your cost, and as you iterate through this, this way. So what will happen? You are using all the 10,000 examples, and that is all that you have in your training data. Then if you perform this step, you are guaranteed that your cost will decrease. So the cost will decrease, definitely it will decrease. And as no matter, I mean, as many iteration as I do, the assumption is it will keep on decreasing, though the rate of decrement, like the derivative, that will also decrease, and it will become flatter and flatter as you go ahead. And this is the usual thing that you see. And if you perform over the whole training data, then this is what you'll see. That's okay. But the problem with this is that if for each update, I have to go through the whole training data, that is 10,000 examples, and that is too costly for us. So we don't want that. So the idea, so the, let's say the workaround for that is that you use something called as stochastic gradient descent. And the term stochastic basically means that here, at least, it basically means that you will shuffle your training data, and we'll see why we shuffle. And then you form what this call as mini batches. So you take these mini batches, and you do the update over this mini batch, and then you do update this mini batch, and then you do this mini batch, and so on. So the update happens every time I read these many, let's say 10 training examples. So there's one small question. So do you think the cost function will decrease?
Siddharth,
Okay.
so
Yeah.
just to reinforce your point. So the update happens only after each mini batches, not correct? Okay.
Yeah, true.
Yeah. Once after you process the deltas for all the examples inside that batch, the update happens only after that.
Yeah, so exactly. So this Nabla W that we were calculating for 10,000 examples, like we calculate for each example, and then we sum them up and we get the net gradient. And that is because, the derivative of sum is sum of derivatives. That's why you can just add these Nabla and for all the examples, and that will give you the net Nabla. So so Nabla of W is equal to summation over X of Nabla WX. Is similar to this thing, and then you subtract it. So, but
should it be
here,
a
what we
sum
are
or
doing is,
an average in the gradient part? I mean, I was thinking it would be an average.
It would be average. Yeah, sorry, it
Okay.
would be average, because there's no point of like, okay, so the 10,000 examples are divided by 10,000, because of course, otherwise this will change by the number of examples that I'm using, and that is not something that we want. Yeah, good point. Okay, so one small thing is, so here we're just using this mini batches. So I have one question, if anybody like to speak for that, answer that. So you have this cost function with you, and you remember that this is defined over the whole training set. So usually we also define cost over the test data. So instead of trying to find the cost over these examples, sometimes to check the accuracy, that how far we have come, we calculate the cost over the training example. And this, you can call it accuracy. It's not accuracy technically, but it's a kind of a measure of accuracy. And if you calculate that, then that will also decrease. So it's important to also calculate the cost for training test data, because of this overfitting, underfitting that we will discuss shortly. So here, at least, you see that we perform the grade, we just sum up, take the average of the gradient for the example in this mini batch, and then we update. So the question is, will the C, the cost function, which is defined as the cost for all the training example, can you be sure that C will decrease if I perform this update? Can you be sure that C will decrease? This just C is defined as summation of Cx over all the examples, so X element of TD, where TD is training data. So what do you say? If I update over one mini batch, will this C decrease or not? Diganta, are you there?
Yeah, I can't be sure. I mean, I'm not sure that it will decrease. It seems to me that it should be possible for it to not decrease.
I think it can go too much in the other direction.
But
Uh,
I didn't get you. What you said?
I think it can go too much in the other direction, right? We are moving
It can
towards
also.
the
Mhm.
Yeah, I
Okay,
mean, other
so
than actually overshooting the minimum, that is a possibility. But even if that doesn't happen, then like uh, two examples can sort of compete, and then it may end up that the final cost does not decrease, right?
so if that's just the thing was that the nabla that I calculate, right? So we are guaranteed that it will decrease over what? Over the function that I calculate. So when I'm calculating the nabla with respect to these examples, right? So it will only decrease with respect to these examples. That is only that what I can guarantee you, right?
Yeah,
This is max that we guarantee that it will decrease over this, but we can be sure that it will decrease over all of these examples,
yeah,
right?
because it might just happen that when we calculated the for the next mini batch, it actually undoes whatever the first calculation was.
Yeah, and remember one more thing. It is doing this one by one is not equivalent to doing it like if I do it for mini batch one, mini batch two, and I do it for all the mini batch till let's say k. It is not similar to doing it for the whole thing. And why is that? Because on each thing I'm updating the weights. In the first part, in the let's say the naive way, I was adding all these nablas, and I was just decreasing, like take the average, and I will just subtract w minus whatever the average I got, and that is how I get my new weights or biases. But here I'm updating on every single mini batch, and that's why doing it one by one over all the batches and doing it in one go, they are two different things. And the point is that I can never guarantee that this will decrease, because let's say I get some weight nabla for this mini batch and I get something for this mini batch. Let's say I just have two mini batch for now. So if I took the whole thing, it might happen that the summation of the nabla for first one and summation of nabla for two gives me something else. And if I like, suppose there was it says to increase the weight, it says decrease the second weight, and this one is saying decrease the second weight and increase the first weight, then they might both cancel each other very well. But if I apply mini batches, then and then I perform the update, then this one will force me to increase the first weight and decrease the second weight. And the next time I perform the this backpropagation, or like the summation of all that gradient and everything on this batch, then that will get a new network. So that's not the same network that we had initially.
Mhm.
So the point is because I'm updating on every batch. So these two approaches are not at all equivalent. And the point is that you cannot guarantee that it will decrease. So what will happen is that let me change the color if there's a way to do this. Okay. So when I'm doing this, what will happen in the gradient descent? Sometime it will increase, sometime it will decrease, and I cannot be sure what will happen. But because we are doing it after shuffling everything, and and also doing like in mini matches, we traverse the whole data set. On the whole, because of like as I mentioned the last time, that it's all based on this law of large numbers on in probability. This all of this will ultimately decrease, but you cannot be sure. So it will oscillate up and down, but it will decrease. The one of the more important thing with SGD is that as you approach your this optimum, let's say this was the point where I wanted to reach, because after that, let's say it's overfitting, and before this underfitting, then it oscillates very wildly. So it just goes back for like really badly. So this is what you get. So uh, as SGD is not like that, okay, you apply it blindly and you'll get the best answer. We have to be very precise, like as you reach the minimum, you know that the learning rate, that is the step size, has to decrease. And that's why we use something called as optimizer. So optimizer uh, changes the rate, this learning rate, as you like iterate and you apply this your algorithm, this learning algorithm. As soon as you are start to reach this minimum, your optimizer will change the learning rate appropriately. I mean, there are advanced algorithms for this. I mean, I'm not very like sure how they implement it. I was trying to read one, but I didn't finish it yet. But the point is that so I'll show you one paper that this is the most used this is called Adam optimizer, and you can actually go through this paper if you want. And so I think I missed something here. Okay, wait a minute. Yeah. So they have given some algorithm, and it's basically, it's like there is some more technicalities in that. So TensorFlow just provides us with some single line of function that you just say optimize that equal to Adam, and it will do. So we need not worry about all this. But the point is that this learning rate thing is very important, that how you change your learning rate, because otherwise, as you reach your optimal, this will start to fluctuate badly, and it won't give you minimum, or it might even shoot you out of your minimum like too much. And you were better off if you stopped earlier. Anyway, so this idea is, I hope, clear. So let's just read some more things. So we partition the data set into mini batches of some particular sizes, and then we apply this gradient descent on each batch, and we update the weights and biases for each batch, and we traverse the whole data set. And when you traverse the whole data set, that is what is called as one epoch. So that will give you one epoch. And the more the number of epochs that you apply, better your model will become. But of course, there are some important thing that we should understand, and that is exactly what we'll discuss now. That is overfitting. So if you iterate too many times, then you might do good on your training data, but you will start to perform bad on your testing data.
When you shuffle the data, after the entire epoch is done, you shuffle and then you do it, or
yeah. So after the one epoch is done, then you shuffle it again, and then you again start the thing. So yeah, maybe I didn't mention that thing. So shuffling is important because it might happen that if you shuffle it, because the actual data that you are going to get, the model is going to get in real life, there's no predefined order in which we will be giving it the data and asking it for prediction. So if there is a particular order, then that might actually negatively impact our model. So what we do is we shuffle it up so that the ordering does not actually makes any difference. And then you do it again and again, and your hope is that it will learn better. Okay, so with the overfitting, so I think this was clear to everyone, I hope, because this is basically just saying that don't do over. So don't iterate too many times. You just iterate as much as it's required. So the thing is that in overfitting, you get great performance in training data, but you get really bad performance on testing data. And the reason for that is that as you are training it too much, your model will start to learn more and more about your, let's say, the noise of the particular training data. So the training data is not something that is actually what you find in your real life. So for example, take the MNIST data. So for MNIST, you have some images like 8, 9, and whatever they have written, and all of them in a particular format. They are not screwed up like, they are screwed up actually, pretty much, but at least if you see the history of it, it was written by some people in one office working, and they just took it and took the photos of writing of these digits, and then they uploaded it. The point is that there is a particular history from where this data came. In the real life, you might not get the similar kind of data. And that's why if you train your model too much just to like, if you're trying to decrease the cost too much, then your model will mold itself to this particular training data, and it will not generalize itself to the actual real world. So that is what we don't want, and we want it to actually understand the patterns and not memorize the data in some way. And we'll see the regularization technique for that. And that was overfitting is. So underfitting is just that you didn't do too many iterations. So you stopped very early. And this way your model will have bad cost on the training data as well as a bad cost on the testing data. So it's like worst of both worlds. So if we don't even want that. So what we want is that we want the best of both worlds. So you just want, this should be small and this should also be small. So that is what we want. Okay. So the technique for this is regularization. And I mean, I won't go too deep into that because we don't have much time, but I'll just tell you how to like, what this is. And to implement in TensorFlow, you just write one line that regularizer equal to something, blah, blah, blah. See it in internet, you can find that here. So the point of regularization is that you have too many weights. So the thing is that your networks there's a big network. There are, let's say, 1,000 neurons here, some neurons here, and it learns the weights everything, but all these weights are, because when you're training it, they just change themselves so much, like they are very high or very low. But ultimately, this will result in some sense that the network learns noise of your particular training data, which is exactly what we want to avoid. And that's why we somehow want to penalize this network, that if you are using too many weights, then it's not good. We don't want that. So we just add this term to a cost function, that is some lambda, and we multiply that by summation of squares of the weights. So what will happen is that my new cost would be the summation of cost plus this thing. This way, when I'm trying to decrease this cost, it will also try to decrease these weights. So it will try that as much as possible that the weights should be near zero. If the large number of weights are near zero, then my cost will also decrease. And remember, if the large number of weights is zero, that is in some way hinting us toward that, okay, this is not memorizing. And I mean, I don't know the quite like the exact maths of this, because even I don't know if it's not very easy to understand how. I cannot prove it to you that why this is working, but this is the way you recognize. So the intuition is this, that you just want the weights to be small. You just want them to be near zero so that you are not memorizing the noise in the network, in the training data. And the other technique for regularization is called as dropout. So it's just that you, for each node, you define some probability, and you say that after a while, after you're learning, after the network learns something during the training, you randomly just cancel some neurons. You just say this neuron will not accept anything, and this neuron will not give out anything. So it will just give out zero, let's say, after it's turned off. So this actually amounts to forgetting the noise. So you are, if your network has memorized some of the noise, then if you just randomly switch off some large number of these neurons, which is called as dropout, then your network will forget some stuff, and it has to retrain itself so that it can recognize the pattern instead of learning the noise or memorizing the data. Okay, so that is what okay, so for this also, there is one paper of this guy, Nitish Srivastava, and it's on dropout, a simple way to prevent your networks from overfitting. So you can read this one. I mean, it's quite an easy read. If you want, I have only read half of it. So yeah, you can go through it if you like and see why this is working and what arguments he's giving in support of this dropout. Okay, so that is for the revision, and I mean, now I'll just go to the code and explain you the assignment and what you are supposed to do. So let's start with this NumPy. I'll call it NumPy. Some people pronounce it NumPy. Okay, so this is just, I mean, I hope, how many of you are familiar with this Python, like the basic import, like what from this, everything, this syntax at least? How many of you are familiar? Can you just like somebody say like, okay, if randomly someone says that I understand that, okay, yeah.
Yeah, we are familiar. I am familiar.
Okay, cool. So if anyone has any question about the syntax or any doubt why is this going this way, then you can definitely unmute yourself and ask. And this is
a question is that what exactly, yeah. I understand the concept of importing and the syntax and everything. What are you importing here? What is CB2? What is P?
Okay. So this is just for like displaying the images. So PIL is Python image library, and and CV2 is computer vision, and maybe the version is 2. And I mean, I don't know why it is 2 here, but anyway, NumPy is numerical Python. So it's a library which allows you to do fast computation. So the point is, in Python, the lists are very inefficient. So you know, the Python lists are like you can increase their size on the go, and that's why internally they are not like the kind of list that we want. So they took too much memory, and the computation are also very slow. So NumPy just collects all the good kind of functions and
you mean to get the details, but these are something independent of it is not any neural net specific that you're training.
No, not at all. No.
You generally think that you want to them to import for any doing analysis or designing any kind
Yeah,
of.
even if you're doing signal processing or whatever, you can use NumPy. So the good thing about NumPy is that it's like the backend is C or C++, I guess, and that's why it's pretty faster than your Python, normal Python. Yeah, though you can actually optimize your Python code also, but anyway. So this is something called as this interface that you're seeing here. I mean, I'm hoping that you all know this. This is a notebook, Jupyter notebook. And if you don't have this software called as Jupyter, which is like given in a package called Anaconda, then you can go to this Jupyter notebook online. There's an online site where they give you these notebooks, though there's a little bit slower than what you will get on your computer. Or you can go to this collab.research.google, and there also you can get notebooks, and you can do it all of it online. So if you don't have Anaconda installed, then use Google or directly Jupyter site. Okay, so how do you like, we start with this. So I say import numpy is np. So now np will be used as a term for numpy. So I say array 0 equal to np.zeros 10, 10, and this is inside a tuple. So I hope you can see it. Let me zoom in. So it's a tuple 10, 10, and if you do it, then it will just give you 0, 0, 0 of size 10 by 10. So this is very important function, because if you so remember, numpy arrays are static. So once you give them size, you cannot change the size. Not unlike Python, you cannot change the size in numpy array. So this function, if you want to convert to integers, let's say, so here you say array 0.s type int, and that will convert all the things into integers. So now they're all integers. Otherwise, they were like, in default, I think it's float 32. Like, yeah. Okay, so these are some important functions that you must understand, so that when you're implementing your, doing your assignment or implementing the backprop and neural network, then they will help you a lot. So there's this function np.random.randint, and it will give you random integer up to 10. And the size of this matrix will be 10 by 1. So if I do this and I print this, so you see it gives me 0 to 10, 0 to 9, I guess. Yeah. So the last thing is maybe ignored. And you get 0 to 9, all the numbers, integers, and the size is 10 by 1. So the 10 rows, 1 column. So there's another function, np.random.normal. So this gives you a normal distribution, and you pass it a mean, a variance, and you give it the size, and it will give you this thing. So let me just print it and show you. So this is a 5 by 6 matrix with randomly initialized weights. Not numbers, actually. I'm calling it weights because that is what you'll be using it for. So when you implement your neural network, you will initialize the weights randomly. And the usual way is to use this function, np.random.normal. Similarly, there's, I mean, this is just to show you how to create a 3D thing. So you just give 2, 3, 4. So this gives you a matrix of this size. Okay. There is one function called np.array that is used to convert a normal Python list to numpy array. So if I call this, then it will just convert this to a numpy array, and that is okay, cool. So if there's any question or any doubt, then just like, this is very basic, so I don't think there might be a question. Just unmute yourself and ask. Be free. So here I'm again saying, so let's talk about accessing. So I just initialize one random array of integers. And if I call this way, okay, so if I call print array and this box operator 1, then this will give me the first row, like the 0 and first. So let's call it first row. And if I want the column, so what will I do? I hope this is the way. So you do colon, comma 1. And if I run this, let's see, okay, so it's giving the first column. So the reason is that colon stands for I don't care which row. So let's just see this 2, 1. So if I give it 2, 1, it will give me second row, first element, and that is 14. Good enough. If I say colon, then it's saying I don't care which row. So it will go through all the rows and collect all the element at the first column and give me a vector of it. And okay, I reinitialize the thing. Okay, and this will give me 6, 6, 15, 80. 6, 6, 15, 80. Okay, so that's easy. Now some important functions. So if you want to multiply the array with some number, you just say 3 into array 1, and that will multiply the whole array by 3. So if I see what is array 1, it is this one, this thing. If I multiply it by 2, I just 2 star array 1, and it will multiply every weight, every number by 2. So I keep on saying weights. Okay. And if you want to apply a function over the whole array, so I have this array, let's see what this array is this, and I want to apply a function, e to the power of whatever the number was. So I just say np.exp array2, and it will apply this to each element. So the matrix on each element, if there is a 2 there, so it will be e to the 2, and so on. So that is it. That is what this one is doing. So if you want to take the dot product, you just call this np dot. So there are 2 dots here, and you just pass the 2 arrays, and it will give you, it will just multiply them together and give you the answer. So let's see this new array 1. So I mean, I don't know where I initialized all that, but okay, let's hope that this works. I mean, I'm not going to go through it, but the point is that these shapes should actually be consistent. So if this is 2 by 5, this is 5 by 6, then your answer is 2 by 6. And that's it. It's just a dot product of matrices, nothing else. So this is very important function here, reshaping arrays. So let's say I give it one single, first of all, I have this Python list 1, 2, 3, 4 till 10, and I convert it to NumPy array. So I call np.array on that. And then I call this function reshape, and I say 5, 2. So what we'll do is it will reshape this data into a 5 by 2 matrix, and it will fill it in this order. This is called C-like order, C language-like order. So this is explained here. And so first of all, it will read 1, 2. So 1, 2, that will form the first row. 3, 4 will form the second row. So remember, this is very important, because when you'll be doing all this network thing, it was very important to reshape your data again and again. It's like necessary to do all this. So just understand this function carefully. Now, suppose you, instead of doing this, so here we are filling the rows and then second row, third row, but you want to fill the columns. So if you want to do that, you just call the reshape function, you give it the size, and then you say order equals, in the string you call f. So it is f for Fortran. So it's a Fortran like ordering. So if anyone of you is familiar with Fortran, you know that in Fortran, the indexing is different. So the first thing you write is not a row, it's like a column and so on. So it will just fill up these things in this order. So if I have this, I don't know what array it was. So let me just print the array first of all. Print array 1. Yeah, so this array was this. And if I fill it in normal way, so it will be, I'm making a shape of 2 by 5. So there are 5 column, 2 rows. So it will just be filled like 3, 7, 0, 5, 2. But if I pass the order equal to f as a argument, then it will give me 3, 7, 0, 5, 2, 0, 0, 6, 2, 9. This can extend to multiple, like if there are dimensions, like if there are 3 dimensions, then something else will happen. So you can just play with it and find it out what happens when you do all this. So so there's one thing, convolution. So I will talk about it later. I mean, at the end, if the time allows, but this is very important, because if you are going to implement your network using this for your project, the final project, maybe you are using CNN, and it's important to understand what convolution is. So we'll see that later. Okay, let me hide this. I don't know. Okay, just give me 1 minute. There's this bar that maybe you guys cannot see. Okay. Okay, let's go to this new network class. So I think this was the code that I was showing you last time, and I don't think anybody understood anything for that. So let's, I'll walk you through it again. And so here I'm just importing some usual stuff. So there's this thing called matplotlib.pyplot. So it's a very big library actually. So from that library, I get this pyplot thing, and I call it PLT. So that's the name. That's like alias for this. So these are just some functions. So let's see just one function. So this is the ReLU function, and I'm defining it as np.maximum x, 0.01 into x. So actually it should be 0. Like it is 0.01 for something called as leaky ReLU. So I don't think I mentioned leaky ReLU like properly. So I'm just gonna put 0 here. So this is basically saying, so when you say 0, it will apply this function np.maximum function to each element of this vector. So X is a column vector, let's say 2, 3, 4, -1, -2. And the function will find out the maximum. So let me find out this. Yeah, okay. Okay, so function, if I give it some input, let's say -2, 3, 0, 5, 6, and I call this np dot maximum over it. So I call this and I call with 0, then it will find out the max of these two things, and just give me the output. So this will be 0, 3, 0, 5, 6. So this is exactly what we wanted for a ReLU to do. So the ReLU is expected to return the max of 0 and that number, and we do that over the whole vector. So this will work over a single number as well as multiple, like if you have a vector here, or even a matrix. If there's a matrix, then it will apply to everything, every element of the matrix. The same thing, max of element, comma 0. That is it. So that's what this will give me. And similarly, you can define the ReLU vectorize or ReLU derivatives. So use something called vectorize. I mean, you can see all that on internet. It's very easy thing, but let's not waste time on that. So I have also defined few other functions like sigmoid derivative, and all of them are like, they work on a numpy vector. So they don't need a value, they work on a vector, and it's faster this way. And let's not worry about these two things. Okay, so I will just comment it out. And this is what you are going to do in your assignment, at least for the first question. And I have filled the code a little bit. So as I told you earlier, that this code is available online, like a similar code, but I don't want you to use that. Try to do it on your own, because I mean, it's very easy to figure out whether you used it or not. So please do not try to like copy it from anywhere. So this, let me guide you through this, what this is doing. So this is a class called network. So how many of you are familiar with class in Python? Like, do you know what a class is? I think all of you must have taken a course on Python, right?
Who doesn't know? Yell if you don't know.
Is there anyone who doesn't know this class thing?
Okay, I guess everyone knows. Yeah.
I guess everyone, yeah, true. So it's good. So this is the init function. So this is just initializer, and we pass the size, and okay, this 2 commas. This is activation function, activation derivative, which I've already defined. These are called default values for the parameters. And if I'm not passing these parameters, then the activation function will be sigmoid, and activation derivative will be sigmoid derivative. So I've defined both these functions here. Okay, and so this is what you'll feel. I think it's very self-explanatory what it's doing. So there's this variable self.cost history. So it is important because one of the question in assignment would be to plot this curve that maybe I shoot you here. So this curve. So you will have to plot this curve on your using your like checked all the training history, and calculate the testing data, the cost for testing data and cost for training data, and you iterate. And as the epochs run, you will using matplotlib, you will plot these two curves and see whether this shape is achieved or not. And it's a I mean, we hope that this is what you're going to get. This shape is what you're going to get. So you just have this variable that can be used to store cost with respect to the iteration number. So as you iterate, you just start to save the cost here. And similarly, you also save the cost for training data. You save it for both of the things. Okay, and this is just trivial things. Here it's important. So you define the number of layers, and this is just the sizes. So if I have, so what is sizes? So you see size is like this. So I pass, okay, let me go move this up. Okay, so if I pass something 5, 2, 3, then it means that I have 5 inputs. Then I have 2 in the neurons in the hidden layer, and then 3 neurons in the output layer. And you're supposed to create this matrix and this matrix. And I think you guys remember that for creating this matrix, I want the output to be these are the weights matrix, of course, and the biases are just a vector. So biases are simple vectors. So you have, for the first bias, you will have a 2 by 1 vector for the bias for this, and the biases for this layer would be a 3 by 1 vector. because there are 3 neurons here, and there will be no biases for this one because, as I told you, this is input layer is like not a true layer. So these are not neurons, these are just inputs. So the weights for this would be, there are 1, 2, 3, 4, 5. So it should be 2 by 5. You see, the weight matrix should have 2 by 5 thing, because I want that when I multiply. So if I have a matrix, the matrix W, and if I multiply that with the input X, then I must get output of these 2 neurons before applying the activation, of course. So WX should be of size shape 2 by 1, and that's why, and this is X is 6 by 1. So sorry, 5 by 1. I'm sorry if I'm using 6. And W therefore should be 2 by 5. So this is the size of the first weight matrix, and this is the size of the second matrix would be like 3 by 2. Yeah, 3 by 2. Yeah, 3 by 2, sure. And these are the two matrices. They are weights matrices, and that is what you will initialize here. So we say self.bias is equal to np.random normal number of neurons, comma 1 for number of neurons in sizes. So remember the number of neurons. So I just ignored the first one. I know this one, and here the layers are, these are the layers. So the first weight vector will be 2 by 1. So this is the way. So use size 1 column. This will strip off the first element, and it will give you everything after it, the 0th element, and it will give you everything after the first and after first one. And you will create the vectors for these sizes, and they will act as the biases. So the self.bias is equal to this one, number of neurons, comma 1. So it's just a NumPy array of size this, and then you create these weights, and these weights are in reverse order. So I say for XY in this, I mean, you can actually, you should go through it and try to visualize what this is doing. But the point is, I hope clear that you just, so if there are 5 here and 2 here, the first matrix is of size 2 by 5. If there is a 2 here and 3 here, then the matrix is of 3 by 2. Yeah, and that's why I say this thing XY, and I reverse the order, and I say create a matrix Y, comma X. So self.weights is a Python list. It's not a NumPy array, it's a Python list. And in that Python list, I have NumPy arrays inside it. And that is what self.weights is. So given this,
I have a question here.
Yeah.
You have chosen the, to initialize, you picked randomly the initial weights. Is that how normally it's done, or are there strategies to pick the initial weight before you do?
One can actually either do it manually, or mostly, as far as I've seen, we just initialize them randomly. But you have the choice to choose the mean and variance that you want to use in the weight. So that is something which is in our hand, that what mean should I use and what variance should I use, and maybe some other distribution for not a normal distribution, maybe something else. But usually it's a random thing, because if you remember this thing, that we need to figure out the minimum, right? And for finding the minimum, we have to, like, there might be these things, right? So if you want the minimum, then it depends on from where you start. So starting from a random point gives you a chance that, okay, you will reach your minimum. Of course, it's not guaranteed. So sometimes that's why we reinitialize everything and do it again. Yeah. Okay. So I think this must be clear.
That is critical, isn't it? I mean, if indeed you want the choice of the initial value also determines whether you will.
Yeah, but I mean, I mean, maybe Diganta mentioned it in the second lecture, I guess, in the second lecture that I gave, that how do you know that will reach the minimum? And I said that there are some papers. So I'll try to put that today, actually, that paper which tells you that no matter from where you start, you are very likely to reach the minimum, or very near the minimum point, for some reason, which at least I'm not aware of. But one can go through that paper if they're interested. Okay.
I do want to add that to answer Professor Srivastava's question, there are strategies though. There are strategies that try to, for example, avoid saturated or dead regions, which would, not let.
This is Sahil, right?
Yeah, this is Sahil. So yeah, so there are some strategies that try to avoid that allow neurons to learn, because they can get stuck. So This is separate from the exploding or vanishing gradient problem that Hithart had pointed out earlier. But there are some strategies that can help.
Okay, go ahead.
Okay. So this function is just feed forward. So I will just explain this function, and the rest is something which you guys will be implementing. And let's just zoom in. Okay, so this is this just takes this self is the useless thing, right? If you know this is just the self parameter. So this in the C++ or Java, you have this keyword. So in Python, you pass it explicitly. It's called self. You can name it whatever you want. There's an X here. So this is the input, and I want to travel through this, do this multiplication for weights and biases and get the net result. So how are we going to do that? It's simple. So you take all the self biases and self dot weights. So you take and you so this zip function is basically just telling you take the first bias and take the first weights matrices. So the first bias vector and the first weights matrix, and then you perform this. So this should be X, sorry. So you do this, you multiply, you np dot w and X, and then you add the bias. That's it. And then you apply the activation function, and that will give you the output. So if you see here, this is what we were doing. So you multiply the weight matrix with the input vector, you get the first output. And then you apply the activation function, you get the output of this, and then you reapply it. The next, you take the next matrix, and then you multiply that. So let me try to make it a little bit of like, okay, I have, okay, what I have, okay, okay. Yeah. So let's say this is the first layer, this is the second, this is the third layer. The matrix here is M1 and it is M2, input is X, and biases are W1 and W2. So M1 is the weight matrix and M2 is another weight matrix. So the first one would be, and sigma is the activation function. So M1X, M1.X, and then you add the bias, and then you apply sigma over it, and that is how you update the first X. So that will give you the output here. And then you take again this, and then you say M2 times X, the new X, let's call it X prime for here, M2X prime, and you add B2 to it, and then you again apply sigma over it, and then that will give you this output. So here we have multiple layers, there are multiple biases, multiple weights. So I just do this in a for loop, and I'll get the output. So that's it for the feed forward at least. And the rest is something that you guys will be implementing, as I told earlier. And I mean, everything is written here. So when I'll send you this notebook, then you can read and understand what you're supposed to do. On the whole, SGD is basically a function which will take the training data, number of epochs, batch size, learning rate, and then what you are supposed to do is, so first of all, find the number of batches. So that is easily calculatable. You just take the length of training data, and then you divide that by batch size. That's the number of batches. And then you make a for loop, and you select the data in that, you shuffle it first of all, of course. And for the number of epochs, so if they are, so you just write something like this. Like, let me just show you. For iter, learn what it in range epochs, so something like this, and then you do something blah blah blah. So this is what you do for each epoch. You will shuffle it up. So there's function, I think np.shuffle or something, I don't remember it, but you can find it out. And yeah, this function is important. So after, on each epoch, you will apply, you will use this function. So apply backprop on batch, and you pass the batch and the learning rate, and that will apply for single batch. So I get one batch from here, and I apply this function, and that will update the weights and biases. And inside this function, what I do, you remember that for the batch, I calculate the gradient for each example, and then I add them up. So you use this function, apply backprop on example, and you pass the example to it, and then it will return gradient somehow, and you have to do something here. And this is what you do. So you apply this thing for each xy, you call this thing x comma y, and you get this gradient, and you save them, and then you also update the gradients here, and ultimately you will update the weights and biases somehow. So that is something that you guys have to like figure out yourself.
So we are not
Okay.
supposed to use computation graph?
No, this is exactly what you're going to do. So internally, this is using computation graph in some way. So you see, when I'm doing the backprop here, so like we are not explicitly generating the graph, but indirectly, that is exactly what we are doing, because that's the way we learned it, right?
So that's already implemented in your code. I mean, that part of
which part?
No. I think let's see. So no. He asked about the computation graph. Okay.
Yeah.
So you had something. Go to the feed forward. You have completely implemented it. Feed forward.
It is implemented.
Correct.
Yeah.
So that's why. Well, yeah. So the computation graph is also kind of needed in the back propagation, no? So you need.
Yeah. So that was for learning how it works, but when we're implementing it, we are not going to like worry about the computation graph and all that business. We just like do this using these matrices, and like when you actually try to encode this, you will understand that it's very easy to do it. And if you do apply, first of all, do this function, and then you do this function, and then this is very trivial function, and then you are done. That is it. And there's test accuracy, and here you just want to like I'll fill up the comment for this also. So it's just calculating the accuracy on that particular test data. Yeah.
So you have supplied the test data also?
Yeah, that is available in the bottom. So I'm mentioning it. Just
okay.
Give me 1 minute. So I just uncomment this. Let me just run everything. Okay, so I'm importing the network class. I'm not like using this one. So that is already written here in the file and network, which I'm not showing you, of course. So there's something called mnist. So it's just a bunch of data. So you just do pip install mnist, and you will get the mnist. And I think on Google Colab, I think it's already there. I'm not very sure, but it should be there. If it's not, then you can learn how to manually import the data. Anyway, so there's something we are doing here. So from this library, you are getting all the training images and all the test images and all the results, test labeled and train labels. All of them are here. And we are performing some normal trivial, like what should I call that? Like pre-processing of the data, so that they become like they come in the format that we are going to. And then the training data is a list of this thing. So this is basically saying our training data is of this format. So it's a Python list of format x, y, x1, y1, x2, y2, and so on. Each of these things is a numpy array, and this is also a numpy array. I mean, even if not, then it's work, but these are numpy arrays, and this is output, this is input. And but all of this as a given as a Python list, and in the form of tuples of x, y, where these two things are numpy arrays. That's it. So this is what you are doing here in this part. So you're converting it to a zipping it. Zipping means just making these tuples, and then you're converting it to a list, and that's what list function does. So this is something which you can figure out by seeing the code. It's not a big thing. And so I'll just show you how this all works. So this is, I mean, if you're doing it, then don't get like this stuff. So there's a star here. Sometimes you see the star. This means that this cell is being processed. So here I'm going to create a network, and this is how we create the network: 784 by 30 by 10. This is just the sizes that we chose. We can change this to, let's say, 10 or 16. I just chose 30. And then you just call this function net. This is the network .sgd, and then you pass the training data, and I am stripping it to 10,000 examples so that it's just becomes a little bit faster, and then you train it over this data. This is number of epochs, like just as this function here, the signature of this function mentions epochs, batch size, learning rate. That's it. That is exactly what we are passing here: epochs, batch size, and learning rate, and you do this. So of course, I told you this learning rate is like very like something which should be changed. And if you have time and if you have the energy to do it, then try to do this. Like, how do you update this learning rate manually? Like in this code, you can do that. The point is, you train that, and it should actually start doing work. Yeah, it's working. So it's finding how many. This is a number of images that it's guessing correctly. So initially, it's getting 2,500. So after first epoch, then it's increasing. So it means that in some way it's learning. And after it's done, I will run this one. But for now, let's go to TensorFlow, because I mean, TensorFlow one is very, yeah.
Expected output stored, I mean, your training data. So because usually you need feed forward gives the actual output.
Yeah, so this is the output that I want, training results. So these are the outputs. And similarly,
we are supposed to use only one hidden network, hidden layer.
you can, like, this is just arbitrary. I told you, like 784 is important, 10 is important. In between, what you use is up to you. It doesn't matter what you're going to use. You can
Only
use
one
16,
layer,
15.
right?
You can use 2 layers. This code that you are going to write, this will work for as many layers as you define here. So whenever you initialize a network, if you write 30, comma, let's say I write something like 6, and then I do this, then it will initialize 2 hidden layers, right? Because the code is written in this way, like when you are going to implement it, you understand it. So it just depends. Like usually for this, I mean, this one layer is more than enough. Of course, like after 25 epoch, you see it's getting 7,300, almost like a pretty good number of examples are like correct, but of course it's not very good because of learning rate. So you see, if you just see this, so initially it was increasing very like fast. So this number just increases. But as soon as we reach the optimum for now, like at least for this, and it's not increasing at that rate that it used to. And that is what I was telling you. So the graph is like this. So it decreases fast and then becomes flat. So by changing the learning rate, maybe if I call it 0.1, then it will learn better. So let me comment out this thing and again call this, and let's see what it does. So now we start from the same network, right? Because I'm not initializing the network again. So it is increasing, but at a very bad rate. I mean, let's say the code is not that good. Anyway, let's interrupt it. And so this is basically plt.im show, image show. And I'm taking an image from the test image, and I'm just plotting it. So this is the image. And let's see what label is and what prediction is. So label is 2, prediction is 2. Good. If I change the I, let's say to 7, 6, 8 or something, label is 9, prediction is 9. So our network is doing pretty good, at least on these. Of course, it will fail on some value. Let's call it 889 and see. So yeah, label is 8 and the network is saying 3. So of course, the network is very bad on, like it's not actually getting really good results, and we'll see. So this one, I'm not going to do this one because I don't think we have time and I don't want to hurry through TensorFlow. So this is something which you should like try to go through it and see what I'm doing. So these functions are like just for helper function. Let's say they're just to draw these pictures, beautiful pictures for this. So you can like visualize better. And then this is the network. I create a network and do all those kind of things. Like here, this is a good example of how you create the data. So here I'm creating the training data myself. So I take some shapes, the square shape and everything, and then I use, I have written a function called get noise matrix, and that will just add some noise to the matrix. And I'm using that to create a lot of data with a lot of noise in it. So so I have four things, 4 labels: noise square, noise cap, noise L shape, and other. So it should recognize everything. And if you go through it, you will understand how you actually create your own data. So it will be helpful for one of the project or assignment that we might give you, that how you are supposed to create your own artificial training data. Okay, and after I have actually trained the network here, so it's getting 175 out of 200 correct. So if I see here, so you can see this is L shape, almost L shape. So you see, even though I have not like trained it that way, so even if this one square is not there, but still saying that, okay, it's L shape. If I change this to, okay, let me do something. Okay, let's make it 0.9 and let's make it 0.9, 0.9 and 0.9. So you see this, now all of these are near 1. So this should be close to a square. But no, it's not a square because these two are like not filled up. So let's increase them to 8, 8, and let's make this 7, and let's see what happens. So it's saying predicted shape is a square. So kind of it's working. So you see, even though this is not exactly like hard coding everything, but this is giving you a good guess what the shape could be. So the good thing is you can see the weights here. So because the network is very small, So you see, these are the weights in the first matrix, the second matrix. So this will help you to understand how we because you cannot actually do all this kind of thing with this one. This is too big, but this is a small network. So you can see the weights manually and kind of realize that, okay, this is how this is working. So it's just multiplying these weights and biases and all. So that's it for this time, for this part, and let's go to TensorFlow.
I have a question. Where are you using the, I guess you're using some TensorFlow functions here or nothing at all?
No, nothing at all. Just number.
Here you're using, not using TensorFlow at all.
No.
But where would you use it? I mean, if you
that's where I'm coming. So
this
is the TensorFlow.
Okay.
Yeah. So we have very little time left. So let's go through it very quickly. It's very easy. So you can find.
No. One logistic thing. So how much time? Yeah, we have to cover TensorFlow also. That is the intention. So there we agreed to go till 5. If that, how much, so without rushing, you go, if we go till 5, I don't know how the rest of the people feel.
Okay, I will finish this in 5 minutes because it's very easy thing, and I'm not going to go too deep in it. And then I'll talk about convolution and give you a basic idea of it. So anybody who wants to stay for convolution because you think that you're going to use that in your project, then you can stay. Otherwise, you can leave. So I'll just give you.
I don't think you can leave because they have not made the decisions on projects, etc. So I guess they'll have to stay.
Okay.
I would suggest, I wouldn't discourage them from staying.
So but I don't want to rush through it. So that's why I'm saying that
I understand.
I cannot. Yeah.
We can do next time. Okay. So the plan so we can decide on what you do the rest of the class today, and then you need.
Okay. So let's do one. Yeah. Okay, let's go till 4:50 at least and see how much we can do, and then we will decide if we can either end. Okay.
So, are you guys willing to stay till 4:50? I'm requesting. I'm suggesting. Yeah. Okay. So 4:50 is the cutoff. Yeah. Okay. Go ahead.
Okay. So for TensorFlow, there are hundreds of tutorials available online. So I mean, there's not much point. So for the sake of completeness, I'm going to just guide you through this one example, and this is available everywhere. Even though I'm not, I don't know from where I got this because this was by some friend of mine. I don't know whether he or she copies it or not, copy it from somewhere or not. Anyway, so you just import TensorFlow, and in TensorFlow there's something called keras, and we are going to use that. And we import this function sequential, dense, dropout. Not using even dropout, I guess, but we are using dropout. But let's say we are not required to use everything from this. Just for example, that okay, dropout is same as the thing that I told you for regularization. That's it. And there's just some helper function that we can just forget that. So MNIST data is already inside, it's downloaded automatically, I guess. So you just call this MNIST equal to tf.keras.datasets.mnist, and it will give you the data, and then you just call this load data function, and then you use this thing. So it gives you 2 tuples, and first tuple is xtrain. So in the first tuple you have xtrain, ytrain. In the second you have xtest, ytest. Okay, so I'm running it, and the second thing, okay, so it's giving me the shape of this thing. So it's telling me in xtrain I have 60,000 examples. Here I'm reshaping the xtrain data, and so it is converted into one big matrix. So it's all in one big matrix. So here you see xtrain.shape 0. So because that's 60,000 example, then the matrix, xtrain matrix would be 60,000 by 28 by 28 by 1. Because 28 by 28 is the size of one image. And you choose this. By 1 is just because it's grayscale, so you have 1 channel. So in your normal images, you have 3 channels, right? There are 3 channels, RGB. So your thing would become here 3 in the case of RBJ, but here we have just 1 channel. So it's just some reshaping and all. This is also the same thing as we did earlier. I don't know if I mentioned it, but this is just because this representation is from 0 to 225. And so you divide by 225 because, 8 bits. So the images are 8 bits. So each number here in the matrix is from I think 0 to 255, yeah. And you divide by 255 for the normalization, and you get a number from 0 to 1. Now this is the important part, and this is all that I'll just try to go through it slowly. So here we have used something called convolution, and I will explain what convolution is if we have some time. It's very simple. I just don't want to get too much into it, but just the basic. And then there's something called max pool in 2D, and then you flatten. So first of all, you say model equal to sequential. Sequential means that you will be adding layers to it one by one. All the layers will be added, and they will be connected like this. So this is what you are expecting from this sequential thing. That as I call this function called model.add, you are expecting that it will first give one layer, then it will connect the second layer to it, then the third layer to it, and all of them will be connected to each other. This is what this add function automatically does for you. So you just say first layer is convolution layer, then there's a max pooling layer, then you flatten it. So flattening is just that you have image, it's a 2D array. So you use the flatten layer, is just kind of converting it into a flat column vector. And then the dense layer is exactly what we will be implementing in this one. So all this thing that we are doing here is a flat, they are dense layers, because there is no like convolution or max pooling. So it just calls something else dense layer. And then there's a dropout, ignore it. And then there's another dense layer. And here you have this soft max function. So softmax is used to, like when you want to do this categorical classification, so you use this softmax function. So it will just convert whatever the output was coming, it will convert it into probabilities. So if the output was something like whatever 2.0, 3.9 or so, blah, 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 you apply the softmax, then it will convert it to something 0.1, this is 0.8 and something. So, I mean, you can read about it more, but it's basically converting it to probability vector, so that you can classify the object, that what is which object it was, using this function called argmax. So you just take the maximum value, and whichever row has the max value, you say, okay, this is category 2, this object is from category 2, that's it. Okay, so this is what you're doing here. And now you just call this function. So ignore this one for now. This is just to load a saved model. So you say model.compile, and then you pass it a loss thing. So loss is how you're going to calculate your cost function. So cost function, loss function. So here we are saying is sparse, categorical, cross entropy, a big word for a very simple function. Search on internet. It's just trying to calculate that, okay, you have in your output as a probabilities and you wanted something else. Then we use mean square in our thing. So here they are using something called sparse categorical cost entropy. So if your classification has so multiple classes, then you use sparse, otherwise you use categorical cross entropy. I hope the name is same, but I think categorical cross entropy is used if you have 2 or 3 classes that you want to split your categorize your data into. Then you use optimizer. Adam, I told you optimizer is basically something which uses the learning rate. So what learning rates, how you're going to change your learning rate. So you can even pass it a constant learning rate using something, I think tf.sgd, and then you call something learning rate equal to 0.01. I mean, I don't remember exactly, but this is how you can even pass that particular thing here. But mostly we use Adam because it's very efficient. Then this matrix. So this matrix tells you how to calculate your accuracy. So, I mean, of course, we are passing accuracy here, but there are many, many ways for calculating this thing, because your output is coming to something, your test data is there, and you want to calculate how good I'm performing on my test data. Then instead of usually accuracy, what it does is that it calculates how many prediction were accurate. So if I wanted this image to classify as 2 and my output is 2, so I get a score of 1, let's say, or inverse a score of 1. If I wanted 2 and I'm giving you 3, then you give me 0 score, and then you add up all the score, and that is what my accuracy is. At least here. But if I want something else, then just search this thing on internet, tf.matrix. So TensorFlow matrix. So what are the metrics available? And you will find out there are like 20 or 30 of them that are easily available there. Okay, so if you just run it, so this is model.fit. This is just compiling the model, and this is calling that, okay, fit the model. and you pass it the train, X train, Y train. So X train is the input, Y train is the outputs that you want, labels. And I'm saying epoch equal to 1, epochs equal to 1. So you can pass 10 or 50, whatever you want. And if you don't want to do this again and again, then you can save your model by calling model.save. So remember, model is not like a general name. So here we said model equal to sequential. That's why I'm using model here. So model.save, model.h5. So it's just some arbitrary thing. You can even write model, it doesn't matter. Maybe h5 is some word that you use. So you just save it. And next time when you're using the model, you can comment these out and you can just load the model directly. Model equal to load model, model.m5. And of course, you also comment this one. So this is how you do this. And I mean, now you can predict it using this thing. So I have not finished it. So if you pass it one image and you convert it into a given shape, let's say 1, 28 by 28 by 1. So this predict function actually takes multiple images, so an array of images, and it will convert all of them at once, because usually we want that whole test data to be predicted. So I'm giving it one image of 28 by 28 size in one channel. Of course, one channel is there because it was already defined in the beginning that there's be one channel. And then you call it and it will say, okay, 1 point. So the value is at index 0, 1. So it's saying that image should be a 1. I don't know whether image was 1 or not, but you can actually try to do this. I think this model is overtrained, so it is giving you a completely wrong output, I guess, because let's run and see. So it was an 8 and it's giving me a 1 because I trained it too much. So I have applied this function almost 5 or 6 times, I guess, this function. That's why it's performing very bad. So it's an example of overfitting. So my model is actually doing pretty bad because it's overfitted. Anyway, so this is how you use this in TensorFlow. And
what are they supposed to do with this as part of their assignment?
Yeah, so if you are going to implement a bit complex neural network, then you can use this thing. And for your verification part, you just want to wait. So there's some function, I mean, I don't remember exactly, maybe it's called get weights. Let's check if it is true. Yeah, so it will give you all the weights, and you will save these weights and biases. Actually, I think it's also give you biases. You will save that in one file, and then you will apply your whatever this verification that you're going to do. It will you can apply that on this.
So let's get to the verification later on. But as part of this programming exercise, I mean,
okay, no, nothing for this one. There's nothing. So it's just because I wanted to cover all of this.
Okay, so but what they can do is to get familiarized, acquainted with this code, correct? Mm-hmm. So they could then.
Yeah, so this one, so second assignment that I was planning to do, I think that is in TensorFlow. That would be in TensorFlow. That is about predicting the frequency of a.
Okay, so then we could think about that and then make it.
Yeah.
Meantime, they have to, if they want to experiment with it, you're saying that they are welcome to do it, correct?
Yeah. And I'll be sending all these notebook files to you, and you can play with it and maybe try to find out how to fix this model so that it predicts this 8 as 8. I mean, you see there's some function here, you will understand from what we are doing. So this image is, I have drawn this image, so I converted it to grayscale, and then I resize it to 28 by 28, and this is what the resized image looks like. And then because we trained a thing for 28 by 28, so you can only use that size, and then you call your model for this image. So you should go through all this, try to fix this model so that it captures this 8 correctly, and
but that could be an exercise if indeed you just made an assignment.
I don't want to make an assignment because no, I don't think it's a good assignment because they don't need to do much in this.
But you have to explain what is it that they wanted. I mean, you want them to change this so that they can get the correct output as close.
Yeah, so maybe change the layers, maybe change something here, and play with all this kernel size and all.
Yeah, I'm okay with not calling it as an assignment, but when you, so just I want us to be clear as to if they want to do something, to describe what it is that they have to.
Yeah, so as far as this is concerned, you just have to figure out what to change in all of this, and maybe use some other optimizer and do something, and so that it figures out all these things better.
Yeah,
it's just for your hobby exercise. It's not
regularization, but there's nothing, that you mentioned that is available. I mean, because
so here we are using dropout. So this overfitting is due to because I call this function too many times, because this model is like I had this from a long time back, and I have called this function multiple times. So I think that's why it's overfitted. I can delete the model and do it again, but it will take like 5 minutes, 2 or 3 minutes to train it. So I'm not doing it. The point is this dropout is there, and there is something called I think bias regularizer or something, and you just when you are using this, I think here in the layer itself you add that. So in the dense layer you just call something, okay, let's blah blah blah, this regularizer equal to something. I mean, I don't remember exactly, but you can search on internet how to add this, and you just pass it L2 or L1 and it gives you the regularization. Anyway, so here you are only supposed to fix this so that it identifies the images that you are writing, and try writing your own images and try to see if it's getting it correctly. But of course, this one that we had earlier, let me see if I can switch to it. Yeah, so here you just have to fill up this code and so that all of this works. So the point is that this should work. Everything after it should work properly, and it should predict things at least to, there was some images which are correctly predicted. So you see, this is wrong, even this is very bad image. So what you can expect from it. Let's see for 2. So network label is 1, prediction is 1, that's cool. So, and remember, this is not using any TensorFlow or anything. It is just something which we did from scratch. And we only used NumPy, which is just a numerical Python library. So it will give you a good insight on how it's all working from inside, provided you don't actually copy from anywhere. I've repeated that many times. And do see this example properly. And this one is just basics. Okay, so I wanted to show convolution. So I think, I don't know, Professor, I wanted to show something in convolution. It's just 5-minute thing, but I don't know like whether the people will stay or they have time to stay. So what, I like some feedback. So should I take 5 more minutes or?
See, if it is something that we want them to, potentially use in
actually,
on,
so
in designing the thing, then we'll wait, because I think in the modeling, there's an example of convolution that Madhukar will be giving as well. So you might as well
skip it.
No, not skip it. Okay.
Okay, explain it.
If you have to motivate, okay, what does convolution do?
Yeah, that is what I wanted to do. So
those kinds of things, okay.
Can anybody like just say that will they like it to like? I mean, that's why I want to give you a chance that if you, because Madhukar will do it, then maybe he will revise everything. But if you want right now, then just say that, okay, we can wait for 3-4 minutes and I can explain that.
I want to give a quick review. Is that okay, guys? So 5 is a real cutoff, okay?
Yeah, just like tell me. And of course, if there's any question for this assignment, how you're going to do this, you can ask me. So, and of course, try this. And if you have any question right now, then you can ask. Okay, so anyone like, can you, do you want this convolution thing just for 5 more minutes or 4 more minutes?
Yeah, sure.
Okay, so somebody's saying sure, so good. All right, so it's of course optional because you might not end up using this. So it's about this thing. So when you remember when we had an image, this was the image, and this was the network. So I flattened it up and I passed everything on this was the input, of course. So I passed one by one, sorry. And in the second layer, everything is passed to every neuron. So you see every neuron in this layer is getting all the 784 inputs. So this is what you do in the flattened case, right? So that's the basic thing that we do in the flattened case. We just flatten this and then we pass it. But the problem with this is that you lose something called as local or spatial information. So you, because you know, if I have an image, let's say there's a guy who is smiling or something, and you are trying to see whether he is smiling or not, you don't want this whole, there's a neuron here. You don't want this neuron to accept everything from the whole image. You just want it to somehow capture this particular part, that, okay, only this part is going as an input to this neuron. Or let's say a bunch of neurons, they're only getting this part and they're not getting the rest of the part. So this is the idea behind this, something called this convolution. So the people who know, like, this is some math stuff. You also have a convolution of functions, which is written as an integration in, like, when you have continuous function. But here we have a very simple, representation for it. And it is like this. So it goes like this. So you have this matrix, which is the image, usually a 2D image, or we can also call it 3D image. In ways, like, there are channels, right? I told you. So there are RGB. So you split your image into 3 parts. So the first is R channel, there's a green channel, there's a blue channel, and we just care about one of them for now. And you have this image, okay? So what you do is, so there's some image. Just look into this particular small portion. So these pixels are like this. So this is 1 pixel, 2, 3, 4, and there are multiple pixels here. I take this part and I multiply a particular numbers with these things, some numbers with this element-wise multiplication. So it's not a matrix multiplication. So what I multiply this with is called as kernel. So I multiply it with the kernel. Let's say the kernel is this, -1, -1, -1, 0, 0, 0, 0, 0, 0. Let's call it +1, sorry, not -1. Yeah, I call it 0, 0, 0, +1, +1, +1, 0, 0, 0. All right, and I apply this, I multiply this to the first patch, okay? What will I get is, if there's a black, let's say it's a grayscale image, so there's a high value here, 1, 1, 1. So if there's a 1, 1, 1 in the middle, then all of this will, these will remain 1, and everything else, these will become 0. Okay? And then I do this for the whole, move this thing, kernel, this way, and I again do the same thing. And I mean, we keep on doing this. We actually sum up all these together, and we get one number here, and then we perform some operation on it. The point is that you are, in some way, you are trying to capture a local information. You are not using the whole image directly. You are capturing some local information, and this kernel is just multiplied and shifted. So the amount that you shifted by is usually called as stride, and then you go on the whole image, and you keep on doing all this, and you get a new image after doing all this. And that is what convolution does. So it's, in some way, it stores, it gets you some information about the image, like it's like applying a filter. So it's actually called apply filter. So I'll just show you the function for this.
So this is done as a pre-processing step before you feed it to the network.
No. It's part of it's part of network. I'll tell you, like, in a little while. So let's just see convolution using CV2. So I read an image here from CV computer vision library, and then I convert it to grayscale. Here we are showing these few buffaloes. It's a 300 by 300 image, and then I define the kernel as this. So that's what I had in the Wikipedia page that I had here. Let me see if I can reach there. Okay, no. Okay, yeah. So these are the kernels that they're given. So you can use them for edge detection, sharpening the image, and all of that. And what you do is you just multiply this kernel, and you convert it to, first of all, I take this image and I take this matrix and I convert to a 3 by 3. So this is, I'm just storing this matrix, okay? This one. I just stored this matrix, and I call this function cv2.filter2d, which is like applying convolution, and I use this image and I apply this kernel over it. And when I display it, so I get this. So it's detecting the edges. So there's a lot of like, you can read more in signal processing, why exactly all this detects these edges. So it's kind of to a certain extent, just see. So if there's one pixel here, okay, just go to the fellow, let's say. So if there's a one pixel here, what I'm saying, what you're saying is multiply that by 8. So because we have an 8 in the mid, so for each pixel, multiply that pixel by 8, and you take all the thing around it, okay, and you multiply them by -1, and then you add up everything. Okay, so now just think about it. If I'm at this boundary, what will happen? All these things in the upper part, because white color is, let's say, 0 and the black color is 1. So all this upper part will become 0, 0, 0. So let me show it here. It's pretty easy to understand. So you have this image. Let's say I have this 3x3 image, and this is all what is black. Okay, this is black part, and this is white part. So I have the weight -1, -1, -1 here. Let's say the values here are the white color is actually 1. Actually, I'm saying opposite. So I don't remember how they stored all this, but I hope it is. Okay, so anyway, let's just do this. Let's say it's 1, and these are 0.2 or something around near 0.2. So when you do all this, so this is multiplied by 8, and rest of it is added to it. So if everything else is also equal, let's say 1, 1, 1, 1, 1, 1, 1, and this is also 1, then you get 8, 1, 2, 3, 4, 5, 6, 7, 8, -8, and that you get 0. Okay, so if everything is 1, 1, 1, 1, 1, then you get 0. Effectively, if you are at a pixel which is surrounded by the similar pixels, your net result will be 0. If you are at a pixel which is not surrounded by same pixels, then you will get some value there. And that is why this kernel is actually giving you these edges. Because if I'm at this her ear, at the boundary of her ear, then everything here will not cancel out the 8 times of this value. So I mean, you can actually just play with this. Let's use 0.5 and see what happens. If I do 0.5, it gives me something else. If I make this also, let's say +2, let's see what happens. It gives me something else. So I mean, it's really fun if you go change these kernels and see how different kind of things you are going to get if you just change this kernel. The point is that this is used to detect what is called a feature map, and this is the feature map of this. So you apply multiple such kernels, and you are, in some way you are collecting some information about your image, and then you pass those images to your. So if from one image I create, let's say, 16 different images, and all of them are detecting something. So one of them, let's say, is detecting the edges. One of them is detecting, let's say, something else, like the internal part of this thing, like the part which is usually black. And then you pass all of this data together to your flat neural network, a normal neural network, the feed-forward one, without convolution, and you just pass that to it. And now the expectation is that this will be able to learn better from this. And that's it, what convolution does. So convolution layer is like, you don't actually have to specify this kernel. This is to answer the Professor Srivastava's questions, that you don't actually specify the kernel. What you do is the network learns these kernels. So you just mention that, okay, I have a convolution layer. This is exactly what we're doing in this part. We're saying it's a convolution layer. There are 28 filters. So there are 28 type of feature map that it has to learn. And kernel size is 3x3. And what we are saying is figure out what the weight should be. And it will use different weight for different parts. So it is not even going to use the same weight for all the parts. So if I have a big image and I'm using 3x3, so it will learn a different weights for this, different kernel for this, different kernel for this, and all of them will be like stored in the network, and then it will apply this thing. So this is what convolution does. So if you want to know how you actually implement it, it's very easy. So just imagine one neuron. What does one neuron do? It will multiply. So
okay, now I have to. So you're going beyond 5 o'clock.
Okay. Oh, sorry. I didn't notice the time. Yeah, sorry.
I think this is interesting in the context of making some interesting examples in the project. So let's revisit this thing. Okay. So I think you should
get
a reference for this, and I don't even mind spending some time in the next class, the beginning of next class, to to do, or
Cool. I'm sorry, I didn't notice the time. Sorry, I'm over it again.
so let's
I'm sorry, but
let's end
yeah.
here. So I think the basic idea, I hope you guys got. Okay, so you know, maybe we can even make that as part of the TensorFlow example that they will be working with. Okay, if we
Yeah.
have a separate assignment.
So just one thing, if you have any question, you can stay and ask. Otherwise, it's already like I said, it's end. It's like end of this class. So, but if you have any question regarding this, you can wait and ask. So I'll be here for 5 minutes, 2 or 3 minutes. Otherwise, everybody else can leave.
So I have just one question about the cow picture example you showed about convolutions.
Okay, let me go. Okay.
There, I mean, when we apply the kernel, then we may not get something that is within 0 and 1, right? So there is like how when we're displaying the image, what is happening to the out of range values?
Yeah, so normally when you do this image from array, and if it is out of bound, then it shows just white color. Okay, it's like
So it's
over
clamping.
the +1. Yeah, it's like clamping, but of course you can perform the normalization yourself if you want to before showing the image. It is possible to do it, but here I'm not doing that because usually the weights are chosen such that you don't get such weird things, big numbers.
Right.
Okay, the kernel is usually not like 100, 200, like this kind of matrix. It's very like using one or something which you know that okay, this will work. Okay.
Yeah, but the weights, Hitat, I mean, if you want the network to learn the training part, to learn the weights for the kernel, you'll have to specify what features that you care about, no? So for different...
that is exactly what we do. We are not doing in deep learning. So if we specify what we are doing, then it's not like, it's not learning by itself. So we just specify that you need to learn 32 filters or 28 filters and go on of 3 by 3 size, just find it out. We don't specify what features. So it might happen that the image that you get by the first convolution layer is not like getting edges. So it's getting edges for this part of image and maybe getting this part of image, because here in the normal convolution, we have the same thing, right? Same kernel for all of them. I mean, there's a possibility of like changing all this. Like it's not very fixed, but I mean, maybe in the next time I can explain it better.
Yeah, I think so. I think, see, there is some thing that I'm not clear about. So something you have to decide what is the box size or something like that.
Yeah, that is exactly what we specify. Yeah, the kernel size that's defined here.
The size is
3 by 3. Yeah.
So when we say that there are 28 filters that it's learning, so does that mean that we're learning 28 different possible sets of filters for each point for the image?
Yeah. Yes. Exactly. True.
So it's like learning. So it's applying. So basically 20 times we're doing the same thing parallelly on the same image.
Yeah, so you get 28 feature maps, and then you flatten them up, and then you apply the normal your dense layer.
Right.
Yeah. So the thing is that the hope is that this applying all of this will actually capture the local information about the image, and it will not like lose the information. Like if I just flatten it directly, then it might happen that thing. I mean, I don't know. Maybe Sahil mentioned this, that if I don't want this part of image to interfere with this part of image, then I can just say that only this part will go to one neuron and this part will go to another neuron. And this part will not go to the second neuron because this part has nothing to do with the output of this neuron. Let's say the second neuron. So this is what we are trying to do with this kernels, this future map. And then you do something called max pooling. So I'll do it next time, maybe if like beginning of the class if it's important. But for now, I think it's clear what convolution is doing.
okay. So any other questions?
If there's any question, then you can ask. And if you want to wait like for this, because you need to implement this code, remember, and that has to be done by next, I think we'll decide the deadline, but it should be next
When do you want them to submit?
I think by next Tuesday or next Wednesday, before the next class,
1 week.
next week class, sorry, next week class.
But I think we should certainly have a TensorFlow assignment as well. Okay.
Yeah, we can discuss that after this. Okay.
About it and then do it. Yeah.
Okay. If there's any doubt with this, then you can ask. If you think that you will be having problem with it, and even if you get stuck, feel free to get some hints from me or Madhukar or anyone, maybe Professor Shivas, for at least for this something. And if you are like exactly doing all this and you're stuck at this coding, then you can contact me directly. Okay, so I think we should end it if there's no question. Just one last thing was that this convolution layer is not very special. So it's not like you have to do something more for it. So it's just like a normal layer. It is just that you are not connecting every neuron to all the inputs. So that is all it's doing. You are just connecting one neuron to some specific part and that's it. So it's like the same structure. Everything flows similar to the last time. There's just very simple minor change and it gives us too much actually in terms of efficiency. Okay, so I think we should end it. There's no questions.
Thank you. So I'll see you Thursday. Yes. So Thursday, Madhukar will correct, Madhukar. So you will
Friday it will be, yes.
Friday, correct. Start introducing, talking about how to model this using SMT logic. Okay, both neural networks and some correctness properties. Okay, so that's the. Okay, I'll see you Friday. Thank you. Thanks for your patience. Bye.